But basically where we're at here is the, kind of the halfway point. And to be honest, we're over halfway. We're gonna be able to spend more time late in the year reviewing, some more work time, packets. It won't be quite as concentrated. We'll spread it out over more time, probably as we get towards the finals. But in the first couple days of class, we talked about rate of change, slope, instantaneous rate of change. And then we also talked about areas. Remember we did those areas? Remember we did the area kind of underneath some graphs, and we talked about what that meant. Okay, that's what we're getting ready for now. So we were talking about rate of change and slope and all that. And then we've really exhausted. We went through all the different uses and applications and how derivative can come into play, related rates and optimization, the chart, all the math examples and the theorems, right? And we just took the midterm with all the different types of problems that involved using the derivative. Okay, so now we go into the second part. Now, the nice thing about this is so much of it relates back to what we already know. Okay, so therefore, if we really understand what we've already learned with derivatives and so forth, that's going to make things easier. And if we are struggling with it a little bit, we're going to have a chance to continually get that reinforced and still make sense of it. Okay, so I want you to look at this situation right here. If I gave you this information right here, okay, about a car, we just took every second, we took a read. And this was the velocity in feet per second, right here. Get your calculators out. We're going to need them again later anyway. We're going to use Give me your thought. Now, there could be more than one answer, and there's no one right answer. There's one answer that's the most popular generally. But there's a lot we don't know. We don't know how fast the car is going in between those seconds, right? So there really is no right answer. But give me your answer or answers, possible answers, for how far this car traveled in those 5 seconds. Okay, I'll give you a couple minutes to play around here with the numbers and see what you come up with. All right, what do we got? Somebody got a number for me? 230. How much?
46.
230. Battery's full.
Yeah.
Yeah, it's so funny. You get in that test mode, it makes it look like the battery's full. 230. What?
46.
46. Wow, those are long ways apart. What else?
56.
How much? 56. 56. 210. How much? 180? 180. One what? 195. Okay, 46. What was the rationale for that one?
I added up velocities. Did its average velocity over 5 seconds.
Okay, so added them up, got the average. Okay, so I think you're missing one piece though. So if you added those up, that'd be the average velocity per second. So you'd multiply by 5. Let's do that. So that's 230, right? So wouldn't that be 230? 46 times 5? 46 times 5 would be 230. So you would agree with the 230. Okay? Where'd the 56?
I did like 38 divided by 2.
Oh, I see. But here's the difference though, because 38 divided by 2, it's not doing it for 2 seconds, it did it at 2 seconds. Does that make sense? So to me, you were finding like an average. Yeah. Okay. Okay, so now we got 4 numbers that all seem to be kind of in the ballpark with each other a little bit. Okay, so who said 230? Okay, how'd you get 230? You added all 6 of these numbers together.
Yes, sir.
Now, why'd you hesitate like that?
Assuming it's a stupid.
I like that honest answer. Okay, I thought maybe it was because of the word 6 when I said 6 numbers. And this would be, again, there is no right answer, right? We don't know what's happening in between there. But let's agree on one assumption, that it's going from 20 to 50 and never going backwards. How about that, right? So it's going to go 20 to 30 and then 30 to 38, 38 to 44, 44 to 48, 48 to 50, right? Not slow down, right, as far as go negative and do something crazy. These are only 1 second intervals, okay? So my problem with the 46, like averaging those 6 numbers or getting the 230, this would just be one fault of that, would be that those were 6 velocities, but were any of those for a full second, or could they all have been for a full second? They couldn't all have been for a full second, right? Because we only have a 5-second interval, but we have 6 different velocities, right? Now that's because you have the one at the beginning and the one at the end, right? So let's move on from the 230. Not that it's bad, it's right in the ballpark with all the others. So who said 210? Jaden, how'd you get 210?
I added up all of the distances, assuming the same velocity. So I added up all the velocities after 0.
So you added up these right here. So in other words, at time 0 it was going 20, but you're assuming it's accelerating through that, right? Through that second. So that would be like assuming it went 30 feet per second for the whole first second. Right? Would everybody agree with that? And then it was going 38 the whole next second, 44 the whole next second, 48 the whole next second, and 50 the whole last second. And that would add up to 210, which would be a little bit like what the guys were saying here. But I think with 230, you're almost using one too many seconds in there, possibly, right? Okay? So I see 210. What about 180? Allie? Seriously? Oh, that's funny, because what has anybody done? Well, take what Jaden just said, except kind of reverse the thinking. What's that? Yeah, don't. So if you said, okay, at 0 it was going 20, and let's assume it went 20 that whole first second. And then it went 30 the next second, 38 the next second, 44 the next second, and 48 the last second, right? And then right at the end, it got up to 50, but we won't count it because that was the end. Does that make sense? Those 5 numbers add up to 180. And then who said 195? Well, how'd you get 195?
I just took the middle of her, I guess, out of each of them.
Okay, well, and isn't that the average of these 2 numbers also? Right? I mean, on the one hand, we didn't use the 20, and we got 210. We didn't use the 50, and we got 180, and we average them. So what she's saying is, if it was going 20 at the beginning of the second and 30 at the end of the second, is it reasonable it was going 25 for an average? Does that make sense? So let's say it averaged 25 feet per second for the whole first second. So that means it went 25 feet, right? And then the average here would be 34, and the average here would be 41, and the average here would be 46, and the average here would be 49. And if you add those 5 numbers up, you get 195, right? So I think any of those are reasonable. Any of those are reasonable. Probably the most common one I get over the years whenever we talk about this one is that. I think a lot of people tend to think of averages, and they tend to average in between them. Okay, but they're all good. And actually, all 3 of those numbers are good numbers to talk about here for what we want to do next. Yes? What would I have put? In my infinite wisdom, probably the 195. But again, that's making an assumption, right? I mean, now, physically, could the thing have been, going 20 the whole first second and right at the end instantly jump to 30. I mean, not really, right? I mean, that's kind of crazy, but it could have been going constant and then hit the gas and then go constant and hit the gas, right? I mean, maybe. So without knowing more information, I'm not sure there's any one of those any better. This one just might be maybe the most realistic. Now, so let's assume then, let's make this assumption that it really is a smooth acceleration. Would, just a nice, smooth, no sudden changes, just a smooth acceleration. Would this be the description of a smooth acceleration, what Victoria said? It would be smooth except where? At those points, right? Because when it's during the first second, when it's going from 20 to 30, it's speeding up, right? Now during the next second, is it speeding up as much? No, it's only going to increase by 8 feet per second. So it's increasing at 10 feet per second, right, as it's moving along, and then all of a sudden for the next second, it's not going to be as much. So it's going to be more like this. It's going to be more like, okay, it's going like that, and then it's going like that, and it's now kind of, it's going like that, and it's going like that, and it's going like that, and those are going to be like straight line segments. There would be sharp points. If I was going to graph that, there would be sharp points there, right? So what Victoria was saying is like an average here, and then an average here, and then an average here, but there is kind of a little bit of a sudden change right there. So if we were really going to assume a smooth transition, then this graph would be a curve that would be concave down, like so. If it was truly smooth acceleration, it would be a curve and it would be this. Now, if we let's take those three numbers we had, the 180, the 195, and the 210. Let's do the 195 first. The 195 would be, now I'm going to make this obvious, that would be this, right? These would be straight lines between here, not curves. Okay? Now, and since the black is concave down, it would have to curve above the red, right? Everybody agree with that? So the black is going to be above the red. Now, so let's take Victoria's calculation that she made there. I claim that she was really doing a trapezoid area when she did that. Now, I'm guessing she wasn't thinking of it as a trapezoid area. She was thinking of it as an average, right? But think about the calculation for that. It would be 1/2. This height is 20. This height is 30. Those are actually the bases of the trapezoid. And this would be the height of the trapezoid. And isn't that give you 25? Isn't that give you the average? Okay? That's the connection we want to make here. So by doing those averages, right, that would be like adding up the areas of 5 trapezoids underneath this velocity curve. Now, we did that the second day of class and the third day. We had graphs, if you guys remember.
I was wondering if I could interview you and a couple of your students for a video.
Not me, but maybe a couple of my students, maybe. But not right now.
Right.
Could you come back here maybe in 20 minutes?
Yeah.
20 minutes or something.
All right, thank you.
And if you guys want to say no. All right. So anyway, these trapezoid areas are just the averages in between there. But the second, third day of class, we talked about how the area underneath a velocity curve was the distance we traveled, right? The area under a velocity curve was the distance we traveled, okay? Now, if you think about the units, 20 and 30 are feet per second, right? And the 1 here is seconds. So this would be feet per second times seconds. If you take feet per second times seconds, jeez, what is wrong with this? Quit it. There we go. Feet per second times seconds, you get feet. Okay, makes sense. All right, now let's do what the other scenario we were doing. Okay, let me try to, there's no way I can do this twice. Oh, gosh. Trying to make this concave down. That's not right. All right, so now let's do the one that was 180. The one that was 180, assume that it went 20 feet per second the whole first second. Wouldn't that be a rectangle then? 20 times 1, 20 feet per second times 1 second. And then assumed we went 30 the whole next second. And then assumed we went 38 the whole next second. And then assumed we went 44 the whole next second, and then 48 the whole last second, and we didn't even use the 50. Now, back up to this one. So we said 195. So Cody asked me which one would I use, right? 195. Well, none of them are right, are they? If this is actually a smooth acceleration, the red represents 195. What would the actual distance be then?
Plus a little bit away.
It would be a little more, wouldn't it? It would be whatever this little bit that we're not accounting for, right? So if the area under this curve would be the distance traveled, 195 wouldn't quite get it. 195 was not a bad answer, and it's reasonable, but it wouldn't quite be probably the distance traveled if this was truly a smooth acceleration. It would miss it a little bit. Now this one's going to miss it a bunch, right? Remember, this was the 180. So it makes sense that the 180 is lower. It's what we're going to call an underestimate of the actual area. And then if we go with the 210, the 210 would be the reverse of that. The 210 would be this rectangle. The 210 would be, okay, let's go 30 the whole first second, and 38 the whole next second, and 44 the whole third second, and 48 the whole fourth second, and then 50 the last second. And now that's going to be an over approximation of the actual area, right? So trapezoid was definitely better, probably, if that's what was going on. Okay, anyway, what's the point of this? Well, because of what we talked about early in the year, the second half of the course is about areas and what their meaning is. Now, of course, the big thing, and Thursday's kind of one of the big days of the year, quite honestly. It's kind of, well, it's a really fun day for me. Mathematically, Megan's ruling, right? It's mathematically a really fun day. You know, I don't know what you guys will think. We'll see. But it's where we kind of tie this idea of how in the world is slope and area, how can those two things have anything to do with each other? Yes?
It's a fun day for you because you can use the heck out of us.
That's part of it. No,
You
this,
like watching our faces, or is it fun?
no, that's every day. That's just every day. Yeah, we'll see. Well, we'll see Thursday when we get to that. We'll see Thursday when we get to that. So here is the area. This is the idea, and this maybe says, hey, area under the curve might be worth something, right? It tells us something. If nothing else, it tells us this distance traveled if you do the area under a velocity curve, right? All right, so in your notes, here's the symbol that we'll use. We've already, at the beginning of this year, we called it the definite integral. Right, and second day we had that worksheet, or second or third day we had a worksheet. We used the term definite integral to mean area. Okay, now we have an actual symbol to go with it, this kind of S-shaped thing. You see there with the A and the B on it, the f of x and the dx. And I got a picture to go with it there. And what it means is, now notice I wrote the word signed in there, the signed area between f of x and the x-axis. The signed area between f of x and the x-axis.
Do we use this a ton?
Use what? Yeah, that little thing. You mean, do you want to be able to draw it well? Is that what you're saying? Yeah. This symbol we use a lot.
Okay, so that's what on all the packets there.
Oh, yeah, in the package, the problems we skipped, you saw it a lot of times, yes, for sure. The whole pretty much second half here is pretty much about integrals, yes, okay? And we'll go through much the same thing we did with derivatives. We'll talk about them mathematically, what they mean as it relates to things we've done in the past, and then we'll get into uses and problems we can solve that use the idea of the integral. Okay? Now, signed area means that you can actually have positive and negative areas. Okay, which is weird when you compare it to geometry. In geometry, we didn't have, negative area. That didn't make any sense. But we do here. It's the area between the curve and the x-axis. Now, the dx. What do you suppose the dx means? Well, what does it mean in dy over dx? What's a dx mean, basically? Well, with respect to, right? So the dy is kind of like derivative of y with respect to x. The dx just kind of means with respect to. So it doesn't mean derivative, it just means with respect to. So this is saying the area from A to B underneath, a lot of times we say underneath f of x. I don't like underneath because if f of x is below the x-axis, it's actually above. It's between the curve and the x-axis is where the area is, okay? So the dx just kind of is tacked onto the end. Don't worry about it right now. We'll talk more about it later, okay? It just needs to be there, though, okay? Now, sometimes we leave it off. Sometimes we write integral of f. Just like sometimes we write y prime and f prime. We don't write f prime of x. It's kind of the same thing. Sometimes we just do that and leave it off. Okay. But if you're going to write, integral x squared, we want to have the dx on there. Okay. So that's what will happen. We'll have a function in there, and then the dx came at the end. All right. Now, you might want to throw this picture on there as well. Again, just to show that sometimes you get negative area. So if we were and the way we read that is we read that the integral from A to B, the bottom number we read first. So we would like for the A to be to the left and B to be to the right. The integral from A to B. Okay, now it's not always written that way. And we're going to talk about that here in a minute. What happens if that's the case? Okay, sometimes it's written right to left. Okay, and we're going to talk about that here in a second. Okay, so area below the x-axis negative, area above positive. All right, yeah, let me just show you that right now. All right, so all right, here's a picture. You don't need to draw this or anything. Now, this particular picture is being drawn with straight lines and circles. Why? Because the only thing we know how to do area of right now is geometry shapes. Okay? X squared, a parabola is not a geometry shape. So we don't know how to find that area right now. So if we get one like that, we'll probably just have to be counting squares or estimating the area. Okay, but if I do the area from A to B, that would be this area right here. And that, as you can see here, is negative. The area from -5 to -2 is a negative area because it's below the x-axis. If I do the area from A to D, if I go all the way, this negative area, now I'm picking up some more negative area. But now I'm picking up some positive areas. So see how this area is now getting less negative and then all this positive area? So eventually, by the time I get all the way over here, I've actually got positive area because the positive area outweighed the negative area. Okay, another interesting one to look at is from B to C. What do you suppose this area is going to be? Just going to be 0. The positive and the negative is going to cancel each other out. And so that area actually counts as a 0. Okay, now watch what happens when we go backwards. Look at the area from E to D. What's it say? It says negative. If you go backwards in your integral, remember the bottom number always we read first. So when we read this integral, we would read this from 9 to 7. Well, 9 to 7 is going backwards. Then the areas are opposite. Kind of makes sense. If you go backwards, they're opposite. So if you go backwards, this is actually a negative area. Okay? So then things change if you go backwards, all right? And so likewise, if we go over here from B to A, if we go from B to A, that's actually a positive area, okay? That's an area of 6 because we're going from right to left on that, okay? And when I say we're going from right to left, I'm talking about up here in the notation, -2 to -5. -2 to -5 is going right to left, going backwards, okay? Then the areas are opposite. All right. So let's take a look at a problem where you might actually have to find an area. So you could write this problem down here. Okay, so what if I gave you this right here? So now here in the beginning, the only way we really have to find exact areas is geometry. So if we get a problem like this, we want to graph it and see if it makes geometric shapes. Now, the only way we're going to get geometric shapes is if we graph lines or parts of circles. That's the only thing that's going to create a geometric shape for us. Okay, well, this is going to be lines because the absolute value is a V-graph. What is this? A V-graph and what's happening to it? Down 3. So if we take the V-graph and go down 3, and you don't have to, I've got my grids here, but these would be a slope of 1. You don't have to make it real fancy. Okay, now I need to go to 1, 2, 3, 4, 5, 6. Okay, so here's there, and then -3 is right here. Okay, so we're talking about this area right here, -3 to 6, and you just shade it in and then calculate it. It's just 2 triangles. So what is this? This is a triangle that's base is 1, 2, 3, 4, 5, 6. Six by what? 3. So what's that? 1/2 times 6 times 3 would be how much? 9. But it would be -9, right? -9. So that piece of area down here is -9. Okay, this piece of area, I should have made that red. Okay, so the red is -9. This piece of area is 1, 2, 3 by 1, 2, 3. So 1/2 times 3 times 3, that would be 4.5. So, and that'd be positive. So -9 plus 4.5 would be -4.5. So this area, so the value of this integral right here is -4.5. Okay, it's just a number answer. A definite integral is just a number answer. It's an area. Just like a slope is a number answer, right? All right. So might have a little bit of that on the homework. Okay, let's write down a few rules here, and that's all I got, and then you can start working. Okay? So now these rules are going to look very, very familiar. These are the same rules that we have with derivatives. Okay? So just go ahead and copy that down, and we'll. Okay, so all the first one says is if you have 2 functions added together, here, you can split those apart. Well, we do that with derivatives all the time. If I'm going to do the derivative of x squared plus 3x, I do the derivative of x squared, then I do the derivative of 3x, and I add them together. Matter of fact, you could put a plus minus here. Plus minus, right? So if you're adding or subtracting, you can split it into 2 separate integrals. I'm going to show you a problem where this could be advantageous here in a second. Also, if you have a constant setting out in front of a function, like if you have 3 cosine x, we always say in derivatives that the 3 just hangs out there. Well, same thing here. Not only does it just hang out there, we can actually pull it out and outside of the integral. And that's advantageous as well. Okay, I'll show you an example right now. Okay, everybody got that? Okay, so those are 2 really important rules that'll just become second nature for us eventually, is we can split apart an integral, and if we got a constant here, we can just pull it out. Okay, so here's a problem. Okay, so here's a problem. So in the directions, right, this is part of the directions. Okay, in part of the directions, they tell us, hey, square root of x squared from 2 to 4 is equal to 10. Now, we don't know what that is. Here would be a parabola. Don't even write this part down, but here's 2, here's 4. There's no geometric shape there. That curved part of that's not any kind of a shape we would know a formula for from geometry. So they're just telling me, hey, that's 10. That area there is 10. They're just giving us that. Okay, then they're asking us, what is this? Well, we're going to use those 2 rules we just learned. One of the rules was we can split this apart. So we can turn this into okay. See what I did there? I just split it into 2 separate integrals. Now, for derivatives, that wasn't a big deal. We didn't really write it out because we just said do the derivative this, do the derivative this, do the derivative this. And that was easy once we had rules for derivatives. We don't have rules for this right now. The only rule we have is we know that means area. And so it takes a lot of work to find the area sometimes. And so actually splitting it apart is good to do. Now, what can we do with this 3 right here? We can kick it out. So we're going to bring that 3 out, and we're going to do this. So now we've turned this problem into this. Right? We've kicked out that 3. Now, what is this red piece right here? This red piece is 10. So this is 3 times 10 plus something. How do we do the area of the function 4? What's the function 4 look like? It's a horizontal line up here at 4, right? This is like y equals 4 here. That's what goes there is the function. Well, what is the area from 2 to 4? That's 8, right? So this integral we can calculate ourselves using geometry. Now we have to do it with a graph, just like here. We had to draw a graph. The only types we know how to do areas of right now is we draw a graph. We got to draw a graph and see what the picture is and use geometry. So we draw a graph, we say, oh, that's a 2 by 4 rectangle, that's 8. So this answer is 38. Okay? Now, kind of fun to check on the calculator. We're going to learn how to do this. This is why I said you could use your calculators here. We're not going to do it on our homework. You're going to have to do this picture. But you could at least on your picture here, you could at least check this. But I'll just show you the calculator. If you go right here, same place we go to get derivative, right down here is the integral. The one that's got the little boxes there by it. Right there. And we can type in a 2. No. I think it's maybe close to 1. Yeah, but it really isn't. And then what do we got here? We got 3x. I can't see mine. Right here. 3x squared, and then we tab. You can just tab to those different boxes. Oh, whoops, what'd I forget? I forgot the plus 4. So plus 4, hit enter. Oh, no, here's why. That was stupid of me. Here's why. I made up this problem. Here's why. Geez, that was scary for a minute. I'm like, wait a minute. All the rules of calculus just went out the window. Remember what we said this was? Yeah, it's not 10. It's not 10. I just was making, but you won't know that in the problems you do, right? You're not going to know. They're just going to tell you, hey, this is 10, right? And then you use it. And that's what we did. Yeah, I should have known better because I forgot that I just made that part up. Okay? Just gave it some number. All right. So anyway, all right, last thing. Here we go. So right here, this says, this seems fairly obvious too. This says if you're going to do the area, the integral from A to B, and we can think area right now, the area from A to B, that should be equal to the area from A to C plus the area from C to B. Now while you're writing that, I'll just say that again. The area from A to B is equal to the area from A to C plus the area from C to B. Okay? Now that actually makes perfect sense if the C is in between those two. Here's the area from A to B, the black. If I take the area of the red, which is A to C, and add it to the area of the green, which is from C to B, the red, oh no, that's not green. It's going to be here in a second. There you go. If I take the red plus the green, that should equal the black. Does that make sense? Yeah, that's just common sense. So that seems like no big deal. The red plus the green equals the area of the black. Now, here's what is useful about it, and you'll see in some problems today, but the C doesn't even have to be in between the A and the B. Look at my bottom picture. Okay? Look at my bottom picture. This statement up here still holds true. Watch this. A to B is the black, so that's this area, right? A to C is the red, that's this area, and C to B is the green, that's this area. Except what? C to B goes backwards, right? So let's see if this really does make sense. So the black area, A to B, is that the red? So the red is this, so that those would both be positive, right? A to B would be positive, the black. The red would be positive, but what's the green? The green is negative because it goes backwards. C to B. So the green would be negative. So isn't the black still equal to the red plus the green? It's still the red plus the green, because the red is positive, the green is negative. It'll just subtract that area off, and you'll be left with the black area. Bottom line is, this statement is always true. It doesn't matter where the C is if the C is in between. So the area from A to B is always equal to the area C, A to C plus A to B. Now why is that a big deal? Because that's going to allow us to rewrite some integrals and make them easier down the road. So you don't have to worry about it too much, but that's what that means. All right, that's it. So homework, we're gonna split this up here a little bit. So here's our new homework sheet for this chapter. Yes, Cody, you can see that there is a antiderivative gateway exam
Soon?
in our future. I don't know how soon. It's a few weeks away. It'd be
What if we just
a few weeks away.
didn't do it?
Bad thing for
I
them.
will, let's not just say we did.
I'll give that consideration. All right.
Everybody
So-
gets the same grade they got on the first.
Yeah.
First day.
All right. Here's what we're doing. Only the very first line, only the very top line, and stop after 36. Stop after 36. Okay, so where it says LH down below, don't do that. That's a packet I'll give you tomorrow, so don't worry about that. So just the very top line, 5.1, stop after 36. All right, now you can work.
Mr. Clark, could you let me know the rules?
Mm-hmm.